All of the data structures we've talked about so far in the class are really just collections of data. So they're holding some data that you can put in and then get out in some order. I want to talk to you in this lecture about a different kind of data structure. It's a data structure that's representing a different idea, a more abstract idea. What we're going to talk about is the idea of connectivity. So we have some things, some of them are connected, and we want to know which ones. We'll look at 3 or 4 different solutions to this problem and we'll analyze them for their performance. So I'm going to do this looking at not only some code, but also some slides from the textbook, which you'll see linked in the lecture notes. The authors of the textbook actually use this problem to introduce the idea of algorithm analysis and the kind of method one can use to start with a not maybe great solution to a problem and refine it until you get a solution that really works well. So we're going to look at this problem, which is we have some set of objects, some of them are connected, and we want to be able to ask the question, are things connected? So here is some abstract sort of blobs in space, and you can see there's lines between them showing that they're connected. And we might ask a question like, is 0 connected to 7? And you can see immediately from the picture they're not, but we can also ask, is 8 connected to 9? And you can see here that although they're not immediately connected, they are connected through some path. So this is something, humans are pretty good at. In the dynamic connectivity problem, what's happening is that things are connecting over time. They'll never break up, but they might connect over time. So in this case, we might add 5 and 0 together, connecting them. We might join 7 and 2. We might join 6 and 1. And then we might ask again the question, is 0 connected to 7? And now you can see, evidently, they are. Note that if I join 2 things that are already together, like 0 and 1, well, they may have a different path connecting them, but they're still connected in the same way. So this particular union isn't changing whether or not things are connected. Connectivity for small examples like this is trivial, but when the examples get more complex, it's not immediate usually to people whether or not things are connected. In fact, this is an amusement for children. We can see if there is a path connecting P and Q. And it's difficult to see these things initially. However, if someone tells you where the path is, you'll find it. Now, what we're solving here is actually a more difficult problem. We're not just saying that P and Q are connected, we're identifying the path between them. This is something you're going to do in data structures too. But for now, we are not concerned with this idea of how things are connected. We're just questioning whether they're connected. And unlike the maze, which is pretty static, we're going to be interested in connection graphs that are changing over time, where more and more connections are happening. This idea of connectivity shows up in lots of domains, such as digital photography, computer networking, social networking, and we're going to model it in an abstract way where the objects that we're looking at, we're asking, are these connected? We're just going to model them as numbers. This is a very convenient representation for us. We're going to use the numbers 0 up to n-1 for in elements. And that's so we can actually use an array to represent something about those in elements. If you actually want to associate this with a real application, such as a photograph or something, you're going to need some sort of association between the numbers and the domain elements that you're interested in. And for that, you can use a symbol table, which you'll learn about in data structures too. But for now, we're just going to think about these numbers. We have some abstract numbers, and the question is, are they connected? So in this diagram, you can see we have 0, which is kind of by itself, 1, 4, and 5, which seem to be connected, and then these other guys over here that are connected. And the way we'll think about this is that there's 3 sets of numbers here. So the set 0 by itself, the set 1, 4, 5, and then the set with the other 4. These are the connected components of this group of numbers. And when we do a union operation, what we're really doing is unioning these two sets, thus the name union operation, where we are joining, for example, 5 and 2. What's happening here in the graph is that we're adding an edge between these. But again, we're not interested in the path or how you get from one place to another. We're just interested in the fact that they are connected. And therefore, it's sufficient for us to just think of this as taking this group of 3 sets into a group of 2 sets. We don't need to represent the actual structure of how things are connected. So these are 2 operations that we're interested in. So there's a union command, which puts things together, and a find command, which asks, are 2 things connected? So when we do the find, we might find whether or not 1 and 6 are connected. Here they're not connected on the left, but they are connected on the right. So our goal is to find an efficient implementation of this idea. The abstract operations that we have are simply going to be that we need to create a set of sets, this kind of union find object. We'll identify up front how large it will be, so the number of elements in this set. But then we'll have 2 operations that are significant, union and connected. So union takes 2 points and connects them, and connected asks whether they're pointed. The point here is that we're going to be dealing with large numbers in general. So digital photographs, as you know, have millions and millions of pixels. And if you're trying to do edge detection and things on them, you need efficient algorithms, particularly if you're doing it in a camera or a phone. The particular kind of applications that we're going to be looking at have a fixed data, like a fixed image, but what they're doing is processing the image as they go. So they're finding connections as they move through the image. And this is why we have what's called dynamic connectivity. So the image itself, we know how many pixels there are, but as we process the image, we might find that one region is sort of all the same color, and so we'll connect all of those elements together. In this kind of application, the operations to do unions and perform find operations or connected operations are intermixed. They're not static, so we don't have a graph that's fixed once, but instead things are being joined over time. And that's key to understanding this problem. There's 2 other operations that are of some importance. One is a count. It's going to tell us how many connected components there are. In our image before, there was 3 and then 2. And we're also going to assign for each one of those connected components a unique ID. So for example, here on the right-hand side, we have 2 connected components, and the ID that we choose is going to be one of the numbers from that component. So we don't know which one, but I do know that the ID of 0 is going to be 0, but the ID of these other elements, it could be any of these numbers 1 through 7. With this in mind, you can see that the implementation of the connected method is trivial once you have find. All you need to do is find the ID for P, find the ID for Q, and return true if those are equal.